Hello everybody, these examples are all about the second law of thermodynamics and entropy. We have now our first question. Find the coefficient of performance and heat transfer rate in the condenser of a refrigerator in kilojoule per hour, which has a refrigeration capacity of 12,000 kilojoule per hour when power input is 0.75 kilowatt. For the solution, refer to figure 5.11 we have here on the right side. Refrigeration capacity 12,000 kilojoule per hour. The power input is 0.75 kilowatt, then we will multiply it to 0.75 times 60 times 60 kilojoule per hour. For the coefficient of performance, the heat transfer rate, and the COP refrigerator is equals to heat absorbed at lower temperature over work input. Therefore, the coefficient of performance is equals to the refrigeration capacity over work. And distribute the given to the formula. We have 12,000 over 0.75 times 60 times 60. We have now 4.44. Heat transfer rate in condenser is initial heat. According to the first law, initial heat is equals to the final heat plus work, where 12,000 plus 0.75 times 60 times 60 is 14,700 kilojoule per hour. Hence, heat transfer rate is equals to 14,700 kilojoule per hour. And now for our question number 2. A domestic food refrigerator maintains a temperature of -12 degrees Celsius. The ambient air temperature is 35 degrees Celsius. If heat leaks into the freezer at the continuous rate of 2 kJ per second, determine the least power necessary to pump this heat out continuously. For our solution, freezer temperature -12, and we will add 273 to make it Kelvin. So we have now the 261 Kelvin. For the ambient air temperature, we have 35, add 273, we have 308 Kelvin. Rate of heat leakage into the freezer is 2 kJ per second. This is the illustration of what we had. For the least power required to pump the heat, the refrigerator cycle removes heat from the freezer at the same rate at which heat leaks into it. For minimum power requirement, final heat is over the final temperature is equals to the initial heat over the initial temperature. So we derive that we have now the initial heat is equals to the final heat over the final temperature times the initial temperature. Substituting, we have now 2 over 261 times 308, we have 2.36 kilojoule per second. And for our work, we will just minus or subtract the initial heat minus the final heat. We have 2.36 minus 2, we have 0.36 kilojoule per second or 0.36 kilowatt. Hence, least power required to pump the heat continuously is 0.36 kilowatt.